Hello. Hello. So I hope I'm audible, and we have a little late start today because the bus was very late for me. We have a little late start today because so yeah. Uh, Yesterday we could not solve any problem, and today it seems that we can. Okay, so okay, anyway. Okay. So we have this problem, right? Walk problem. So we have a simple directed graph n vertices 1 to n, and we are given an matrix where ij, the ijth cell represents if there is a connection from I to j. Okay, and if it is 1, that means there is a connection, and 0 means not. So we need to find the directed paths of length k in the graph modulo this. Okay, or also same as multiple times can be traversed. Constraints are given n, k. Okay, anyways, so we had something like this. This is the test case that this is given, or maybe it is something that I came up with. So anyway, so let's say we have a test, a graph like this. Okay, just a second. Okay, let's say we have a graph like this. Okay, and here we want to get the k is equal to one path, all the paths which has length 1. So how do we proceed in this? Basically we can have this path. Okay, we can have this path starting from 1, we can have this path starting from 2, and we can have this path starting from 3. So we will have 3 paths, and if we have k is equal to 2, then okay, in this case in k is equal to 2's case, again we can start from 1, go all the way up to 3. Okay, start from 2, go all the way up to 1, or we can start from 3 and go all the way up to 2. So these are all path 2 length paths, right? So you see what is happening. If we start from a path, if we start from a vertex u, let's say, we are going to its neighbor. Okay, we are going to its neighbor, and from there we want a path. Let's say if we want a k size path here, then from its neighbor we want a k minus 1 size path, because we already included 1, right? So it will be k minus 1. So again, when we'll then go to, let's say, x or w, and from there will go for a k minus 2 path length. Okay, and in this way we'll go till we have a path of path length 0. Okay, we will go till we have path length 0. This is how the you can say this is how we are calculating. Alright. So if you see, how can we write a recurrence relation for this? Okay, suppose we want, suppose we have a DP state like this, U okay, and K. What this tells is number of paths starting from U of length K. Okay, the transition will be base case is simple, right? Base case is what? For every node, 0 path length will be 1 only. Okay, the transition will be simple. If we want to calculate for U, right, we need to have all the k minus 1 path lengths from its neighbor. Okay, so basically we are doing this dpv k minus 1. We are going to the neighbor of U, and then from there we are checking for all the k minus 1 path lengths, right? So this is a recursive call. Okay, and if you want to write a recursive solution for this, you can. So basically there will be what the base case will be, or let's say we have dp like this. We will have the start. Okay, we will have k, and if k is 0, then we'll just return 1. Otherwise we'll have our answer. And what we'll do is, for all neighbors of the starting vertex, what we'll do is we'll add the answer like this: dp and neighbor and k minus 1. Okay, and we'll return answer. Okay, so something like this. And for all the vertices, we'll add it. Okay, so this will be our answer. Okay, and a brute force. But what is the time complexity for this? Time complexity is a lot actually, because we can have n neighbors, okay, for each, and we are going till k depth. So we can have okay, so there can be n branches, right, and this branches itself can be k length. So n to the power k, and then we are doing this, so k plus 1, something like this. Correct, right? I think so, because it is possible to go to the as you have already visited, right? So that option is still open to us. So if there is a graph, fully connected graph, for each vertex we can have n options, right? And we can go till k steps, right? So of course n into n into n into n into n up till k times, so n to the power k from this recursion itself, and we are doing n iteration here, so n into n to the power k, so basically n to the power k plus 1. So this is not feasible. Let's see let's try to expand on that what transition formula. Okay, so the transition we have now is basically this dpu k is summation of v belonging to adjacency of u dp v k. Okay, so if we expand it, we are iterating on over all the adjacent vertices of U basically. So suppose if we want to calculate, for dp 1 and length k, so what we'll do is we'll check all the adjacent of 1. So how can we check that? From the adjacent matrix only. So in the matrix, if we have 1, that means there is a connection. If we have 0, that means there is no connection. Since it is a binary value, it is actually possible to just multiply it with its respective dp value. For example, if the matrix is adjacency, so we are doing just this multiplied by dp 1 k minus 1. Okay, since there is no self loop, so it will be 0 and this term itself will have no meaning, but for expansion sake I am writing this. Similarly, from 1 to 2, is there any edge? And if there is, we will have all the edges from 2, all the paths from 2 of length k minus 1. So similarly we'll do all this adjacent 1 and nth vertex and multiplied by dpn k minus 1. Okay, so this is the first iteration. So basically and if we want to calculate for dp2k, it is same, just this will be different, right? It will be 2k minus 1 and similarly all the it will be 1k minus 1 still, and just the copy paste, but just the this part will be like changed. So similarly we can calculate for all the vertices. Okay, so if you know about matrix, right, we can actually represent this whole calculation in a simpler and more readable format. Yeah, this entire n line of equation we can convert it into this. Okay, so basically we are calculating dp1k we also have dp2k till dp nk. Okay, so we have all this and it is simply equal to the matrix that we have, okay, and multiplied by what, dp1 k minus 1 dp2 k minus 2 and all the way up to dpn k minus 1. Okay, so how matrix multiplies is basically this row, like this will be a 50 at max 50 cross 50, so it will be n cross n only. Okay, so n rows will be multiplied with n columns. Oh sorry, n columns will be multiplied by n rows. Okay, and that value will be added as this value. Okay, similarly this second one will be multiplied with this and it will be counted as second value. So at the end of the day we will have a matrix of size n cross 1 basically. So since this is n cross 1, the result will also be n cross 1 matrix only. But we know that this thing is also a problem in itself. Okay, this thing is also a problem in itself, right? So we can further expand this and we can write it as a n cross n whole to the power k multiplied by dp1 0 dp2 0 all the way up to dpn 0, which is nothing but our base case, and that is 1 only. Alright, so essentially what we are doing, we are calculating the given matrix to the power k. Okay, so we are just calculating given matrix to the power k. How do we do that? Well, there are different ways of doing this, and the one I came across is matrix exponentiation, and I don't know how to use it, so we will go through some blocks maybe. Yusako has problems with it, I don't know. I never really liked its tutorial. Okay, bro. It's not loaded. Let me zoom it. Okay, so we have a basic introduction. Okay, it is kind of like a binary exponentiation, I think. So what in binary exponentiation, what we do is, instead of calculating a to the power b directly, what we do, we check whether b is odd or even. So see, if b is odd, okay, in that case we can write a to the power b as a into a to the power b minus 1. Okay, and now b minus 1 is an even number. B minus 1 is an even number. So in that case, what we can do is, instead of calculating a to the power b minus 1 directly, we can do a to the power b minus 1 by 2. We can calculate that and we can square that. Okay, squaring is easier than because it is simply multiplying. So we can do that. So we are essentially doing that only. So I think, okay, I don't think I need any tutorial for this. Maybe I can just implement it. So binary exponentiation, how that will work? I don't know. We have a matrix a to the power k. Okay, n cross n basically. So we can write it as either 8 into a to the power a into a to the power a k minus 1 by 2 a into a to the power k minus 1 by 2 square, or a k by 2 to the whole square, something like this. Okay, so basically, if k is odd, if k is even. I know I have written it as in a very complex manner, but it is very easy to understand actually. So suppose we want to calculate 2 to the power 8, right? So instead of calculating 2 to the power 8 directly, we are breaking it essentially. We are breaking it as like this, 2 to the power 4 square of 2 to the power 4. Okay, and this thing is basically better understood in this what I think. So we want to calculate 2 to the power 5, let's say. Okay, so it will be 2 into 2 to the power 4, and this 2 to the power 4 can be written as 2 to the power 2 square, and this 2 to the power 2 can be written as 2 to the power 1 square, and we can simply return if 0, so it will be returned as 1 only, and 1 square if it is returned as 1, no, we can write this as 2 into 2 to the power 0. This will be 1, so we'll return 2. This will in turn return 4, and this will in turn return what, 16, and then we will return altogether 32. So this is how it basically works. So that's how it basically works. So I think we can wait a second. You can just solve this then. Okay, we can solve this. We have nk. Okay, we will have k as well. We'll take input in and k. We have the matrix and we should it's one only, but if we have it integer, that I don't think that 32-bit they're not saying that 32-bit is the answer will exceed 32-bit. So we will have a this adjacency matrix, and after I don't know how to resize a 2D matrix or vector in C++. Internet is slow for some reason, I don't know. My stream, how is it? Fuck. Hello. Hello, 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 hello. Okay, we are back. Actually, there is some issue with my encoder. Basically, OBS is acting up. I don't know why. It is not sending enough data to be able to run a consistent stream or maybe smooth stream. Okay. Resizing it. Okay. Sorry. Adjacent dot resize n, and for I0 n adj I dot resize n, and probably we will do the same here. I don't want to write this, so I'll just copy it. I'll copy it again, and I'll take input in the adjacency matrix. All right, we are done with the input. So this is basically one index zero index matrix operation. All right, So we'll solve it with zero order manner only. Paste this, and I'm going to make a helper. Okay. So what we are doing is, see, once we calculate a to the power k, we will be multiplying it with this matrix, right? N cross 1. So what this does is, entire row will be multiplied with this column. Okay. So essentially we are just adding this row value. So we can have a matrix only of n cross n, or whatever the size is, and in that matrix we'll store the answer, and then we'll add it simply just we can just add entire values, so it won't be like not a difficult like operation, I think. So getting answer from that is easy, but exponentiation part. It is going to cost a lot of memory, or will it? So basically how multiplication happens is, you choose one point, so it is basically the final matrix location, so I and j, and then you traverse all the values till n or k, and you multiply it and add it, and that is how you get the answer for that one location. Okay, so it is basically a for a simple matrix. The multiplication itself will be n cube. Okay, and since we are doing the power exponentiation part, and it is going to be halved in each step, so it will be like this, log k or base 2. So this will be our entire time complexity. So now I am more concerned about the multiplication, or so multiplication part. So we will be multiplying the matrix at most log k times. Okay, like here we multiplied here, and here. So 1, 2, 3 times, right? And the end the answer was just returned. So log base 2 5. So basically 1 plus log base 2n, that will be the time complexity at most for binary exponentiation. Of course, for matrix it will be n cube into 1 plus log k, but yeah. again. So we will need a helper. This is my first time actually writing a matrix exponentiation code. So how do I can have answer, and can have I can have a function. So basically multiplying, it will take what? It will take a matrix, and since we already have it in the, so it will take only the power, and if the power is if the power is what? If the power is 0, in that case we can just return a matrix with all ones. This is called an identity matrix. Okay, not all ones, but just like identity matrix, you can see like this. We can return a matrix like this. Okay, so we will return an identity matrix. So return identity matrix IM. We will have an identity matrix here. But we need a size M and right. We'll create one. We'll have a matrix IM is equal to, or it has been created, n comma vi n, and all the values are 0 only, and for like all the diagonal elements we are going to be setting it to 1, and then we'll return the matrix. Otherwise we have two options. If P is even or if P is not even. So if P is even, in that case we need to return okay. So this is not how we need matrix multiplication. So we will have one matrix, we will have second matrix. Okay, so we will create a new matrix, and the size will be what? The number of the size is like the number of C size will what? If you have a matrix, if A is the size of 1 cross n and B is size of n cross 1, so size of C will be 1 cross 1 only. So the only thing that matters is the row size, number of rows of A. Okay, so A dot size, and the second thing that matters is how many columns there are in B. So like this. Okay, and then we will start with this. We'll have J, and then we'll have K. K will go from same 0 to n. So, and for each K, we will just add ij plus equal to aik multiplied by a kj, and the entire thing will be modded, of course, and the mod is 10 to the power 9 plus 7 only. So mod equal to, so it will be modded, and now that we have this, we will just return the C. Okay, so we have the multiplication, and here, so matrix, we have the power, we have this and this. Okay, if we have a even power, in that case we will return I think I'm doing something wrong here. Yeah, I was doing this. I was trying to do this. Okay. We have this. We have this. So we will have our answer as what? Our result as, say, IM at first. Okay. Uh, probably should. Probably should. Okay. So we have our res as IM initially, and at the end we are going to return res. Okay. So of course we have the power here, and we are going to check for it. What we can do is, if the last bit is basically set, that means we are doing this only, set or 0. Okay, in that case we do, let's say it is not set. So what we do, we will do this, res equal to multiply res and a, or whatever adjacency. Okay, and otherwise we will do adj equal to multiplication of adj and adj only, and we will do p minus minus, and here we'll do p by equal to 2. Okay, so I think this should work, maybe, who knows. So we will okay, so I think we should not. Okay, so we should rather have a temporary which contains, which has adjacent. We will to change that only. Think. Oh yeah, this is the same thing. So this should work. I'm not sure. And we have our matrix exponentiation. pass key and for all the values we will add to answer, of course after modding it. So it will be this and this C. So we have answer as 4. Let's see. The answer is 6. What about this case? The answer is 3. What about this case? The answer is 6. What about this case? The answer is 1. And what about this case? The answer is 10 somehow. So it is not working. This is not working. But this should work. Why? Very strange. So it is a good resource, so I'll save it. But let's go for geeks for geeks. Are we doing something wrong? Yes, we are. Oh, fuck. Silly mistake. Silly mistake. Sorry. 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 Okay. Copy and paste. Verify that I'm not a robot. And see. Fuck. Why? Okay, so I think most probably it is because of the modulo, maybe. The fourth case itself didn't work, right? Okay, okay, so it is modulo. Modulo is 10 to the power 9 plus 7. 10 to 3, 4, 5, 6, 7, 8, 9. It is correct. We don't need you. Or do we? Okay, so maybe this thing will be modded as well. Probably we don't need this thing. So we will mod this, and then we will also mod this. So I think now should work. Why? So he has created a whole class for it. Okay. percentage mod here. So for this, remove this, add this, no change. I think I did the same thing, but it is not working. Why? Okay. This is not an issue, but still. Wrong answer, wrong answer, all wrong answer, please. Oh, it actually gave a wrong answer. Oh my god. Why? So copy paste, bro. This guy also is doing copy paste. I mean, what is this? So basically you do this, and from all this you do this. It didn't work. Okay, addition is changed. Okay, so int add is like we have int I, int j, and if we have I plus equal to j greater than mod, then I minus equal to mod, and we are returning I. Okay, fair enough. We have a multiplication. In this multiplication, what it does is we have I and j, and we're just going to return int of long of I multiplied by j modulo mod. Okay, then we have matrix multiplication, so we'll name it matmul, and here what we are going to do is we are going to add Cij with multiplication of this and multiplication of this. I'm actually just copying and trying to see what I did wrong, because I don't think the solution itself is wrong, it's just the implementation part of it. So that is why. So it is done. Okay, done. This is also done, and when I am calling it, I'll just do a matmul. Okay. Okay, just see, I'm going to do one thing. Paste. I'm going to copy his code, and for sure he is going to get it correct. See, I don't even know what I'm doing wrong. Maybe it's the mod itself, I don't know, but for every other question it has worked correctly. So I'm not sure if it is because of this. See? actually done, bro. Just this one thing. Okay, so what I did wrong basically, because I chose 64 bits, but I was using only 32 bits, so it was actually terminating before executing fully. So that is why I was not getting anywhere close to 9.5 billion, I think. Okay, 9.5 billion. I was only getting till 2.7. So the rest of you know 6.8 billion were not even calculated. So yeah, oh, bro. So yeah, uh, yep. So that was it. That was it for this stream, I think, and we solved it. Uh, right. It's time to end the stream, and I think I hope that you liked the stream if you are watching, maybe. So yeah, I hope you have a very good night and peace out.